Cool. Yeah, let's get started. Thanks for coming, everyone. My name is Pranav. I'm an engineer here at Aleo. And today I'm super excited to talk to you guys about Aleo, the Leo programming language, and just, walk through how we can build private applications on our stack. So let's see. Cool. So Aleo is an L1 with a novel architecture that really enables private applications, but also really a unique point is that we also enable stateful applications as well. And in this talk, we're going to figure out how Aleo achieves that. And we're going to start with some preliminaries. So we'll do a little bit of a review of snarks, look at decentralized ledgers a little bit abstractly, look at the account model, which is a primitive a concept on which most decentralized ledgers are built. And then look at a new model called the record model, new or old, depending on your perspective, but the record model which Aleo uses to really enable these applications. Once we do all these preliminaries, we'll actually write some code. So we'll look at Leo, look at data types, familiar paradigms, and then introduce some advanced concepts that Leo has, including how to program records and how to use on-chain state in conjunction with the record model. And then finally, we'll look at some upcoming things that are happening in the Aleo ecosystem, some new tools that we have on the horizon that'll help developers. And then we'll wrap it all up with an announcement on Z-Prize. So before we get started, just jumping into things, here's a link to some resources to get your dev environment set up. Depending on your internet connection, this may take a little bit of time. So I recommend anyone, especially if you have a little bit of a slower internet, hop here, go to this link, maybe start getting things set up while we talk about, the high level overview. I'll just leave it up for a couple more seconds for anyone who needs it. And yeah, let's get to it. So snarks. So I think it goes without saying, especially now that we're here at ZK Hack, is that zero-knowledge proofs are a powerful tool for building secure systems. Specifically, zero-knowledge proofs are privacy-preserving cryptographic proofs of computational integrity. And if we sort of double-click into that, a zero-knowledge proof is effectively some proof pi, which proves that given some public output y, some publicly known function f, that I know some output, some private input x, such that y is equal to f of x. So the core idea here is that with these zero-knowledge proofs, I can kind of prove to you that I know something without actually showing you that something. In reality, this is all way more complex, and there's way more depth to this. And I recommend checking out resources that are associated with the Zero Knowledge podcast, ZK Hack, the whiteboard sessions for a deeper introduction. But we're just going to keep things at a high level for today. So the first zero knowledge proof was invented in 1989, and the protocol is kind of constructed at a high level as follows. You have a prover with some function f, some claimed output y, and the prover has some private input x that it does not want to reveal. You also have a verifier with the access to that same function and public knowledge of the output. So the prover claims that they know some private input x such that this statement holds. The verifier asks the prover, okay, prove it to me. And the way they go about doing this is with a sort of challenge and response protocol. And eventually, after a couple of rounds of this, the verifier can be convinced that the prover, in fact, does know x. Now, this is a remarkable achievement, but there's still some problems with this construction. And they're essentially kind of lie into these three spaces here. First of all, this protocol is interactive. So it requires for the prover and verifier to be online in order for the verifier to be convinced. And this is not really a desirable property in most cases, in some cases at least. Also, this protocol isn't succinct. So the proof that the actual that the prover sends isn't short, which this is something that can be improved on and is another desirable property. And then finally, this protocol also doesn't have concrete efficiency. It takes the prover actually a very long time usually to generate this computation, and also requires the verifier another, a significant amount of time to verify this as well. So if we fast forward a couple more years into 1994, we actually get the first succinct non-interactive zero-knowledge proof. And in this protocol, this makes some improvements on these problems that we saw before. So in the same way, you have your prover, and then you have your verifier, except your verifier here is much smaller in the sense that it doesn't require as much compute to do verification, which is why we have it in a smaller box here. And when the prover makes the claim and the verifier asks the prover, first, they agree on some, they agree on some random oracle, basically some common transcript, which the prover will use when they're generating the proof, and the verifier will use when they are verifying. And this common transcript basically tells the prover that, okay, these are the inputs that the verifier is going to challenge me on, and tells the verifier these are the inputs that you want to check on effectively. And in using this construction, the prover can then just submit a short proof to the verifier, and the verifier can check it quickly, and this gets us the first ZK snark. Again, this is super high level, but we can kind of operate with this definition for most of today's talk here. And just so that we all kind of get on the same page, what is a ZK snark? ZK snark is a zero-knowledge, succinct, non-interactive argument of knowledge. And essentially, a ZK snark proof is, the proof is zero knowledge, meaning that it doesn't reveal the witness, the private inputs used to construct the proof. The proof is succinct, meaning that it's small in size and verifying it is fast. The proof is non-interactive, like we discussed. The prover and verifier don't need to be online and exchange messages back and forth to perform verification. And the proof is sound. And this is a technical requirement, but at a high level, it means that any statement that can be proven true by the proof system is actually in fact true. So now that we have a high-level idea of zero-knowledge proofs, ZK snarks, let's switch gears a bit and talk about decentralized ledgers, at least abstractly, so that we can kind of frame the problem that Aleo tackles today. So again, I think it goes without saying, decentralized ledgers are desirable. They enable a huge number of applications that we really didn't have before, but they still run into some fundamental limitations. And to really understand why we run into these limitations, we need to take a closer look at how these work. So on the left here, we have a ledger with some accounts, their associated code, and some data. And essentially, decentralized ledgers ensure correctness by re-executing transactions. And so what do I mean by this? So essentially, when a user submits a transaction with some application data, an input, and a signature authenticating the transaction, it's broadcast to the network, and each node on the network re-executes this computation. And if the computation is correct, the nodes agree, and the signature is valid, the state for the application is updated. Now, the problem in this model is that ledger re-execution really hurts scalability. So because every node needs to re-execute on this network, this just leads to a lot of wasted computation. To do some napkin math here, if you had 3,000 nodes on an ETH-style network with 5-second computations a block, this leads to like about 15,000 seconds or 4 hours of re-execution, which can be avoided. And because of this, I think this is a familiar motivation for most of us here, which is why we have constructions like rollups. So we know that we can use zero-knowledge proofs in a way to achieve succinctness, and this is sort of the primary motivation for that. But on another dimension, ledger re-execution also hurts privacy. Because every node needs to re-execute every transaction, they need to be able to see all program state, all user data, input data, output data, basically everything, at every piece of state on that network, and they'll need to see this and use this till the end of time. So fundamentally, in this construction, you can't have privacy, and it really breaks a lot of applications that can't allow this much leakage. So clearly, we do need to improve on this construction. But first, we need to see where this problem is coming from. There's a sort of like higher level concept of why decentralized ledgers, especially organized in a certain way, have this problem of scalability and privacy. And that problem really is associated with the account model. So the account model at a high level is a model for organizing account and application state. And sorry, I'm gonna take a pause before we go into the account model. I see a question on the side. The first question was, will ZK rollups need miners? And really, like, it depends on your construction, but really what you need for a rollup, like fundamentally, is sort of in some constructions, you'll need something like an operator or a miner to make it happen. Either that can be done sort of in a lightweight construction, or you'll probably do it for a whole network, but it's really dependent and you'll still need it. But then these things can be succinctly verified on your target chain. The next question was, will we post this session after and where? I believe this will be uploaded to YouTube, I think within a day or so. And then the next question is, where would I find information about which curves are used with the account to generate a private key? I believe like the source of truth is on our GitHub. I don't know if Colin might be able to link, or anyone here might be able to link the exact curves and their exact parameters. But yes, hopefully that answers your question, and hopefully that'll be answered a little bit down the line. Okay, great. So back to the account model. So the account model is this high-level way of organizing application, user, and account state. And in this model, you basically have a decentralized ledger here on the left that tracks each account's data with some like global data structure, some piece of global state. And for each account, you have its address, its balance, its code, and its storage. And storage is essentially, it's like you can think of as its persistent memory. On the left here, you have a user on the network and the user's address. So when a user creates a transaction, the transaction itself contains the address of the account that they want to interact with, the value they're sending in their transaction, the data of their transaction, a fee, and then a signature authenticating that transaction. And when that transaction hits the network, all the nodes on the network see this, authenticate the signature, and execute this transaction. And if the nodes agree, the account state is updated. So the balance of the account will be updated, and its storage will be updated. This is a very simplified model, but it still highlights what we'll get to, which is the problem with the account model. And it's that, well, first of all, this account is simple. This model is simple. It's really easy to program. It's really easy to use, nice to work with. And it's the one that we've worked with like pretty much so far, especially in like Ethereum style, like more programmable decentralized ledgers. So we do like this model, but there is some problems, like we've discussed before, on scalability and on privacy. So while this model is easy to work with, again, to reiterate, it's not fundamentally scalable and it's not fundamentally private. So let's see what we can do to improve on this construction and see if we can gain some privacy. So what we're going to do in this sort of exercise is we're going to try to attempt to extend the account model with some cryptographic, primitives, and see if we can arrive at something like private smart contracts. The idea being is that we want to hide smart contract data, its usage patterns, while also creating a performance system. So yeah, let's have at our first attempt. So in the previous section, we defined a transaction as this, like data structure here. We're going to make some modifications. So first, let's commit to the value that is being sent in a transaction instead of sending it in the clear. We're going to encrypt the data under some secret key. And then instead of sending a signature, we're going to send a proof. And that proof is going to attest to the transaction's execution, the state transition performed by that transaction. It's going to attest to the fact that it has been performed correctly. And then on the right here, where you have your original model of your account with its balance, code, and storage, instead, we are going to, again, commit to the balance. At the bottom, we're going to encrypt its storage under some secret key. And the key thing here is that we are going to transform the code into a representation that can be reasoned about in a ZK snark. This representation is what we call a predicate, but you can essentially think of it as a mathematical formula that represents the specification of the code. So now that we have all this together, let's see like how it all kind of works when a user submits a transaction. So you have, again, your now modified global state, where in your account, you're only tracking a commitment of the balance, a mathematical formula or predicate representing the code, and then encrypted storage. And when a user submits a transaction, when a user submits a transaction which contains its address, the commitment to the value, the new encrypted data, the fee, and the proofs, the network will then just simply check the proofs. And if the proofs are verified, the account state is updated. And now, if we kind of rewind a bit, we mentioned how ZK snarks give us succinctness, which allows for fast verification. And essentially, what's nice here is that the main improvement in this construction here is that instead of each node having to re-execute computation, they can quickly check that it has been done correctly. And hopefully this should all still be like, familiar, mostly review if you've been keeping up with the previous workshops, as well as the content on YouTube and so on. Now, let's actually kind of double click here and see what we're actually verifying in these proofs. So what we're given is, or input, what we're taking as input is the code, the old state of the account, so its old balance, its old commitment to its old balance, and its old encrypted state. And then we want to make a new claim that the new state is correct. So like the new state is actually, in fact, this new commitment to the balance and this new encrypted values. And in the proof, we're first going to check that the value is conserved. So you're not minting money out of thin air. This would be not great to have. So you're going to check that the sum of the commitments to the balances are all equal to the sum of the new commitments to the balances. And then you're also going to check that the program predicate is satisfied. So given the old encrypted state as public inputs, some other public data that's given in your transaction, as well as some private inputs being the unencrypted state and the actual value of the accounts and the actual data that you're sending in your transaction, you're going to check that the program sort of executed correctly. And when you do so, you're effectively checking that state transition. Now, this model is actually it's fine. It seems pretty interesting. What we do get here is some privacy in terms of our data. So like whatever's stored in the account isn't available to see because we're encrypting them, and we're not storing the balances in the clear. But there's still some problems in this model. The main problem, one of the main problems being that there's no concurrent access to program state. So in order for you to do any of these proofs, or any of these predicates, essentially consume the entire program's old state before updating it and producing a new one, which is then sent to chain and add it if the proofs are verified. The problem with this model here, where you're consuming the whole state and then putting the new one, and they're all encrypted, is that if you have two parties trying to transact with the same program, but there's sort of like a difference in timing, it could get to the point where one party successfully updates a program A, but a second party has read old state. So whenever they try to actually submit their transaction and get it updated, it is invalid, and therefore their transaction's rejected. The only way you can sort of have multi-tenancy in this model is where where party A, reads the state, creates a transaction, submits it to the network verifies it, verifies the update, and then in the second party can then read the new updated state, create a transaction, and then update that to the network. So it's a very serialized model, and it's not performant. And yeah, this is a problem. And then there's no privacy in this account model. So right now in this big ledger, in this big global data structure, each account, even though its state itself is encrypted, its data is encrypted, it's still indexed by address. So although you don't reveal the contents of your application, you reveal access patterns. So every time if I'm user one and I'm interacting with program A, the entire network knows that it is me that is interacting with them, with that program. And so in this case, yeah, you do have some privacy, but this isn't really the privacy that we need. So let's kind of review the properties of this construction. So we have no more ledger executions. We're using ZK snarks to succinctly verify that our program was run correctly. We have data privacy because we're committing and encrypting the balance and the data itself, respectively. But we don't have account privacy, as we discussed, because you can see access patterns. And because a program needs to consume the old encrypted state and produce the new encrypted state and then send that to chain, basically, you don't have efficient state updates and you don't have concurrency. So can we improve upon this model to make this better, right? Like what's the really core of the problem here, and how can we improve it to get some more of these properties that we want? And the issue is that basically in this account model, every transaction needs to consume the entire program state in order to it needs to consume the entire program state. And then also addresses are public. You're still indexing the entire ledger, the entire program state by its address. So there's still just one single place you're looking at when you're actually storing and updating your program state. So the idea here is that instead of like this model that we have before, the key intuition is that can we shard application state such that each user owns their own piece? And if we apply this intuition, we arrive at something called the record model. Before we go to the record model, I see a new question. When can we start doing transfers on Aleo? So people are building wallet applications at the moment, and once there, you have a better UI for doing these transfers, but fundamentally they are possible on our network. The code is all there, and it's just to make this more feasible, we just are looking for we're just improving upon the user experience here. And then just to also call out, once we also start adding support for general deployment and execution of programs, this also becomes much more smooth. The next question is, so what makes Aleo different than other privacy-focused projects like XMR? Sorry, I'm not completely familiar with the core properties of that construction. So, or like, the other protocol. I think maybe someone can cover it in the chat. If not, feel free to ask it on our Discord or Telegram, and we can kind of like discuss that offline. And the final question, and this was my final one before I switch to the record model, is does Aleo offer internship programs or junior positions for beginners who are willing to jump full-time into the space and learn to contribute? Aleo is actively hiring. We don't have an official internship program. And I think that's as much as I can say on that. We do have our jobs listing on our website, and but we're also always happy to like interact with people new to the space and get them up to speed with our grants program and have a couple other avenues for doing so. So you're not like fully out of luck, but we don't have an official internship program. Great. So I'm gonna keep heading on. So the record model, just to recap a bit, so that we're all on the same page. Account model has some core problems. No actual privacy because of access patterns, and no concurrency, no efficient state updates. So we're going to solve that with this new model or old model called the record model. And essentially, in this model, a decentralized ledger tracks each record via global state. So instead of tracking accounts, it's indexing that by address. The ledger tracks effectively a set of records. And let's see here. So what happens is in the construction here is that you have some global state. For each program, you have its program ID, its code in predicate form. And then you have also a subset of records that are associated with that program. In that record itself, the record owner, the person who owns that piece of data, is encrypted. The record balance, the value, is a commitment instead of it being in the clear. And the record data itself is also encrypted. So there's no information being revealed here. And you have a user here on the left, and a user effectively owns certain records on the network, but that's all encrypted unless a user, queries it and uses or spends a record. So here you have a user actually submitting a transaction, and a transaction is essentially broken down into a number of transitions. Each of those transitions refers to a program that is being invoked, the old records that are being consumed, so the old pieces of program state that are being consumed, the new records that are produced, so the new pieces of program state, and then a fee and some proofs. And when the proofs are checked, if they are verified, the network updates the set of records associated with that program by effectively, adding in the new balance and updating the new encrypted data for each of those records. So essentially in this model, users consume and use records only associated with their context for a specific execution of the program. So by sharding this application state this way, you can now have multiple people hitting that application at once without taking it into an inconsistent state, while still also maintaining privacy as well, which is the core intuition here. And then finally, because the decentralized ledger can enforce stuff like that no record is consumed twice, you don't have double spends of application state, and this is important for ensuring consistency of your application. So what is actually checked in these proofs? Again, just so that we complete this idea, you're taking in as input into this in this proof statement that the code predicate, the old records, and you're producing that, you're making the claim that this computation has produced these new records. And what you're checking is that the balances of the old records and the new records are, the sum of the balances is conserved. And then you're checking that the program predicate is satisfied for all input records and output records. And in doing so, you have this construction that not only has the properties of the previous construction, but also allows account privacy. See, in this case, there's no actual data being revealed in the clear. Like even your owner, whoever owns a record, is encrypted. So no one on the network can see record owners. You have efficient state updates because we've sharded application state. And then you have concurrency because different applications can, because different users can hit that application at the same time and without going into an inconsistent state. And we really get that fundamentally because we've taken stuff from an account model and sharded it into a number of records. Like an entire application state is sharded into a number of records, each of which is owned only by the user of that application. And yeah, that's sort of all the primitives upon which we've constructed Aleo. And the fundamental thing here to call out is that really, so why do we care about accounts and records? The reason is the account model in traditional constructions and older constructions is how we manage global state, program state, right? In Ethereum, all your state is on the network, on an account, and that's used to drive the program execution. In the record model is essentially a different way of organizing things, organizing program state, such that we can do things privately. So, for example, like if you didn't really care too much about having program state, and all you want to do is just run programs and check proofs, you don't fundamentally need this record model. But this record model is key in ensuring that you can start creating applications that have some notion of state. That state can live on chain, it can persist, and be executed over the course of the ledger's execution. Great. Let me take a quick look at some questions here. Let's see. Okay, answered. Okay, so when would we be able to deploy a Leo program and execute it on chain? So we'll talk a little bit about doing something like that on later in the workshop. The short answer, though, is that we're working on it. This is the next milestone that our team is going to be tackling in the phase of our testnet. So more to come soon, but this is the next sort of big thing that we're excited to update people on when we get there. Just a quick thing for the question that was, can you brief us about nodes? If you could just shoot a reply, elaborating on your question, that'd be great. Difference between Aleo and ZK Sync. I think I'll leave that to the chat to actually, correctly answer. I don't want to speak out of turn and misrepresent the properties of ZK Sync. The exact difference between prover and miners, validators and stakers. This is essentially, so the short answer is that provers effectively run programs, validators produce blocks, and stakers stake on the network. There's much more information about this in detail, I think, in our blog posts, and there might be a couple more resources out there. But for this talk, we're not going to dive into that. And then the next question, there's another one. Is that the record model similar to the UTXO model? It is similar. That's sort of the key intuition. You can essentially take the UTXO model and kind of extend it into the record model. Let's see any more. Okay, cool. What happens? So the next question was, what happens when an application needs to perform some actions for the user, since the user is only one in control of keys? So I think if I'm understanding your question correctly, you're asking that, how does an application sort of, execute on the behalf of a user? I think if I'm understanding your question correctly, we'll get to this later in the workshop, but we can also augment the record model with some notion of the account model. So some notion of global state and re-execution by the network to get a hybrid model where you do all your stuff in private that you want to do with records. And then whenever you need an application to perform some actions on behalf of a user, you kind of switch over into the account model-ish, or into some global ledger re-execution, and then do some stuff there. More to come later in the workshop. It's a pretty cool construction. And yeah, more to come. Let's see. So the next question I see is, yeah, I'll leave this I'll leave this up for the rest of the chat, and we'll just we'll keep heading on. So now that we have an idea of all these like high level concepts and we've got some intuitions for things, let's look at what Leo is and how we can use it to actually develop private applications. So this will be the coding component of the workshop. For those of you who haven't gotten a chance to install and set up both the Leo, the Leo CLI, the Aleo SDK, and optionally some VS Code plugins, please go to this link and follow the instructions. There's a specific setup instruction which essentially pulls a script and runs it, and will do all of your setup for you. If you opt to manually build and do things, you might find that you'll have to install some stuff when you first run a Leo program. Don't worry, we'll give some time for that as well. But I'm just going to pause for maybe 2 minutes, 2-3 minutes, let people set things up, and then we'll keep going. And then in the meantime, I'll answer questions. Okay, great. So next question. So is running a client node equivalent to running a full node on another blockchain like Bitcoin? Another word, what is, so let me answer that first piece of the question. Sometimes to run a client, you may need to, you can opt to run a full node, like with any other construction. If you don't want to do something as heavyweight, we are exploring some ideas for light clients. Those just more to come later. Yeah, it's more of we just kind of need to design that construction there. I think the question though, what that question is getting at though, because each client needs to manage its records, it might require more work than a light client in other contexts. And it makes the light client look a little bit more like a full node, but this can be done quite easily, not quite easily, but at least your initial scan of records is probably the most computationally intensive task you'll ever do as a client. But after that, all you're doing is just, getting records that are relevant to you. So that's pretty easy. It's pretty lightweight and doesn't require that much compute. So that was the first part of the question there. Second question part is, what's the difference between a client node and a prover? So a client node can be a prover, but we also have a scheme where a client node can delegate proving to another node with more computational resources. And then that node can execute for you or create the proof for you and submit that to the network. So for example, if you're on a lightweight mobile device, you can delegate to a prover, it'll get the job done, send it to the network, and do it on your behalf. And then, yeah, the second part to that question was second comment there was, I understand the prover is kind of like a miner with Coinbase rewards as incentive. And yeah, that's effectively true. So right now in our testnet, provers are essentially grinding certain puzzles for Coinbase rewards, but the distribution scheme is more unique and I think interesting. I'll leave that for to look at, at some resources on the Aleo blog. One quick thing before I answer one more question is the noise in the background still a problem? Feel free to chime in let me see. Okay, great. Okay, I see a no.
It works. Can't hear anything.
Okay, great, awesome. The final question is that we'll do before I move on is, how could I do data analysis if all the data were encrypted? So this is where you could actually construct some cool schemes. First of all, one thing that I'm pretty excited about, if people can kind of make this happen, is you really can enforce a data marketplace by first principles, because every user sort of owns their own records, right? Like a user can decrypt all of their records, but no one else can see them. Users can submit their data on a data marketplace for just for people to buy and use. And you can probably construct some cool schemes out of that. That will require probably a little bit more cryptography you have to use to sort of allow I guess tiered record decryption, but I'll kind of leave that as an exercise. But yeah, you're right that you won't be able to do just data analysis just outright, just by looking at the chain. And I think this is an important thing to have. It's actually a feature, not a bug, because really if the whole core idea is privacy, this is sort of like fundamentally at odds with it. Cool, and I will leave the rest of the questions for to be answered in in their threads. So I'm assuming everyone's gotten some time to set things up. Let me see if I can get rid of this. I cannot. Cool. Yeah, okay, we'll just keep moving on. Let's see. All right, so now that we have some intuition for the record model, let's take a look at Leo and see how we can use it to develop private applications. So Leo is a high-level programming language that is compiled into Aleo instructions, which is more of like an assembly language, which is then serialized into AVM bytecode, which is the actual format in which programs live on chain, and is the actual format it's used on the network. The compiled bytecode is effectively the format that's deployed on chain and then is visible to all participants on the network. And then finally, the Aleo virtual machine, or the AVM, is a virtual machine which will read AVM bytecode and execute it and produce a proof. So in this workshop, though, we're only going to focus on Leo code. There are a bunch of additional resources on Aleo instructions in the AVM in our developer docs, and you can get to our developer docs via the bit.ly link, but it's also developer.aleo.org. And there's a ton more resources out there, and it's a pretty cool construction. Definitely encourage people to check that out. So with that, let's get started with Leo. Let's create our first Leo program, and and then we'll kind of go through the parts of a Leo program. So for those of you that are following along, open up a terminal window, open up VS Code, and type in the following command. So we're going to create a directory called projects. We're going to cd into that directory, invoke the command Leo new hello world, cd into that. And then we're going to call Leo build, and then Leo run main with these inputs, and you can just use them directly as is. So I'll give people 2 minutes to do something like that, and then I'm going to walk through it with you guys and show you parts of this stuff on my machine. Cool. Let's see. Answered. Okay, great. I think most of the questions are taken care of. For the person who asked about nodes a little bit a while ago, if you can add some more clarifying information in your thread, that would be great. We can get to that question once you do. Great. I'll give people just another 30 seconds. Great. Okay. We have another question. Does Aleo support private state consensus on layer 1? How efficient is it in terms of transactions per second / speed? So I guess to maybe unpack your question a bit more. Oh, did the question sort of disappear? Let me just answer it outright. If we're talking about just how does the network arrive at consensus and how does it relate to state? Well, because all your state is private by records, your networks don't need to re-execute. They're just checking proofs over state transitions. Those proofs are zero knowledge, so they don't reveal any information about your application state. And in doing so is preserves privacy. So during consensus, you just check proofs effectively. Maybe that answers your question. If not, feel free to ask another one. Oh, I see it again. How efficient in terms of transactions per second? I don't have the current numbers right now. I think maybe someone might be able to post it up, but yeah, that's off the top of my head. And then the final question is, what programming language does Aleo use? The programming language is called Leo, and that's what we're doing right now. So yeah, if you get a chance to install Leo, we can walk through the demos all together. So let me do just that. we're gonna create a Leo program and go through the parts of Leo program. So I have the directory called projects. We're gonna do Leo new hello world, and we're gonna cd into this. Cool. So this is sort of the structure of a Leo project. You have a README. The first important piece is you have this thing called a program.json, and this is like your config file for your program. Here, the two main important pieces I want to call out is you have some development accounts, and essentially you have a private key and you have an address associated with each account. Whatever you execute Leo programs in this directory, it's going to use these private keys and addresses. And now you can always swap these out with new values, and you can do that using the Aleo CLI. So if you look at the terminal here, you can do Aleo account new, and that generates a new private key, a view key, and address. And you can swap these out and effectively execute transactions under different identities. The next main important thing is you have your source directory with your main.leo. Here is the Hello World Leo program. So you have a program scope, the scope which defines the body of a program, and you have the program's identifier. This identifier will correspond to a unique identifier for the program on chain. So it's a unique identifier such that any other developer or any other application will be able to find a program via its program ID. Then you have a transition called main. And a transition essentially forms a public interface of your program. More on transitions later. There's actually some deeper concepts here, but for the purpose of this intro, this is fine. So your transition is called main. It takes a public input, which is a U32, takes another input B, which is a U32, and in Leo, inputs are private by default. If you don't put a public visibility on it, it is assumed to be private. And then it produces a U32 as an output. So because there's no modifier here, this is going to be a private output. Then on line 4, you have a declaration of a variable, C, a type declaration. And because Leo is strictly typed, we currently require all variables to be typed, explicitly typed. We are working on type inference, so more to come later. But on line 4, we add we take the sum of A and B and then return C. One question I think seems relevant to answer right now, I think it came up, I saw it a little bit earlier, is are input files being deprecated? This is a great question. We've been going through some back and forth on design here. So for the purpose of this workshop, we don't need to touch inputs. Everything that we will run can be done via the command line. So you're all good to go there. So more to come on inputs. You can track it on the Leo GitHub repository, but we don't need that for today. And then you have a directory called build. Let's actually build the program. So we'll call Leo build, and that's going to populate the build directory. It's going to go do some stuff, invoke the AVM, and build the program. And in the program, you'll have your main Aleo files. This is Aleo instructions. And you have the associated program.json. That's essentially a clone of the one that you saw before. So this is the high-level overview of the high-level anatomy of a Leo project. We're not going to go too much into Aleo instructions today, but you can always find some more information there. But just so that we're all on the same page here, you can run Leo run main, one U32, 2 U32, and you can build and run this program. Cool, great. Awesome. So with that, let's actually go and do a deeper dive of the Leo language. Before we do that, I see that okay, we got some answered questions here. One question, is there a difference in computation cost between a public and private input, all else being equal? Yes, there is, because in your snark, you're going to have to encrypt that value Oh, you said input, but you're going to have to decrypt that input. Same thing for outputs. Great. So let's talk data types. We're going to just do a quick flying tour of Leo and hopefully build an interesting program. But we'll first get started with primitive types here. Leo has some primitive types, integers, booleans, that are probably familiar to most of you. It also has some algebraic data types, fields, scalars, and groups. And these data types relate to the underlying snark construction, and also relate to some of the underlying cryptographic primitives that we have available also to be used in Leo. So for example, in Leo, you can hash, commit, do all that stuff. And these are data types sort of related to that. You also have some specialized data types. Address, it should be fairly intuitive. It's relates to addresses on the network. So Leo also has custom data types, user-defined data types that you can declare in a program. The two user-defined data types are structs and records. For now, we're only going to look at structs. Records actually have some deeper underlying meaning, so we'll tackle them later. So structs are probably declared in a sort of familiar syntax if you're coming from C-ish, maybe Rust. You declare a struct, its name, a timestamp, or a member variable, in this case a timestamp, and then you declare its type. Now, member variables can either be primitive data types or they can also be other structs themselves. So fairly natural interface here. So now let's actually start looking at some programs. Actually, we have a cool question here. Why do we call Leo a language and not a Rust DSL? So I wouldn't call it a Rust DSL. You're probably right in calling it a Rust-like DSL, Rust-like domain-specific language. And maybe you can call it a Rust DSL because it is implemented in Rust, but it's more Rust-like. It's not exactly Rust-like because there are certain concepts in Rust that are as natural to express in circuit-based languages. So for that, I think for the purposes of answering your question, language and DSL can almost be used interchangeably. Great. So let's look at a Leo program here. Here's a program. It's called hello.aleo. And the first thing to call out is we see a function and a transition. Now, in Leo especially, a function is a piece of code that takes some values as input and produces some values as output. And it can be called by other transitions, but transitions actually are something special here, and they're really to do with our programming model. A transition is a function that can interact with on-chain objects. So it can consume and produce records, which are then posted up to the chain. It can also interact with on-chain state, which we'll get to later in the workshop. But there's some cool stuff that you can do in transitions that you can't do in functions. And really, transitions are a new paradigm that are needed to power stateful applications on Aleo. So next up, we have, we see, like we addressed before, we have a variable declaration. It has to be statically typed. Here we have a subtraction operation. And one thing I'd like to call out here is that all default integer arithmetic in Leo is checks for overflow. So the way we've implemented it under the hood is that if you just use the straightforward like standard operations, your overflow checks are built in and it's built to be safe. If you'd like to use wrapping operations, which can be sometimes more efficient, but also unsafe, you can explicitly declare them and use them in, or not explicitly declare them, you can explicitly use them in Leo. But you can find more resources on that in our developer docs. So transitions also have this notion of visibility. So functions just take in inputs, produce outputs, but transitions themselves actually, will be the public interface of your program and will form the actual predicate that you define. So here you're also, for transitions, you can define public and private inputs and public and private outputs. Now, there's also conditional statements, conditional structures in Leo. So you have conditional statements here. One thing about Leo is that you can also return early from conditional statements. So if you're kind of going through a branch, you can exit the branch and exit the program early. And this is just there to kind of provide a familiar ergonomic interface. You also have for loops. For loops here need to have their loop variable statically typed. So you do need to declare the type of the loop variable, and the loop expressions must be integer literals for now. And we're working on extending support there. But here, they must be explicitly declared integer literals. And the reason why is that when the compiler takes this high-level Leo program and turns it into a circuit, it needs to, all the computation needs to be sort of statically defined and unrolled into a sequence of computations, or a circuit, basically. A circuit always has a fixed size. So for that, like, loop literals need to be static integer literals, but they can also be constant expressions. More to come on that later. Leo also has some assert statements that can be used to check certain values or certain properties when we're producing proofs. And if any of these assertions are triggered, the execution halts, and the AVM, the Aleo virtual machine, fails to create a proof. This should just feel familiar to asserts in other languages. And then you also have something like self.caller. This is a special sort of thing we have where you can get the address of the person or the entity invoking this transition, or invoking this transition, and it lets you, create some checks. It can be useful, and we'll see that later. Great. So we're going to get into our first sort of programming challenge, coding challenge. We're going to budget some time for this, and essentially the coding challenge is this. We're going to compute interest. It's going to be simple, but just give you enough to see, just get comfortable with writing Leo. So we create a new the first challenge here is to create a new project titled interest. We saw a couple steps ago how to create a new project via the Leo new command. Second part of the challenge is in that new program, that new scaffolded structure that you've defined, you will replace the main transition with a new transition called calculate. Calculate will take in a private variable principal and a public variable rate, and then calculates the resulting balance after compounding interest for exactly 10 periods. And assume that rate will be a U32. And just for simplicity, we can assume principal to also be a U32. So I'll give everyone some time to work on that. Feel free to ask some questions. I'm going to go through, answer a couple more. And we also have some test cases for you to just sanity check your implementation. The funny thing here is that you're doing integer division, which will have some weird corner cases and won't get the decimal values that you might be expecting. So feel free to check your work with some test cases. Great. Just going through the list here. So first one, is there a way to view the 35 constraints generated for hello.aleo? So one thing I'd like to maybe just call out about constraints in general. So maybe first I'll answer your question directly. There is no way to do it with a tool at the moment. We have a tool internally that we use, and we're going to work on, we are open to releasing it once once we kind of get it into shape for that. So that's to directly answer your question. And then another thing, just to kind of just to throw out there for constraints in general, every proving system sort of has their own stuff with constraints. At least with ours, you should, constraints is a useful metric to use when you're trying to optimize your own program locally. So if you made your MVP1 of a Leo program, it's producing some number of constraints. Well, a great way to see that you've actually made an improvement is try another implementation and see if you have fewer constraints. More about like comparing constraints across languages is very, I'd say, it's sort of a poor metric of comparison. I think you find that like um, numbers are represented differently, and there's certain like internals to like making stuff work with program state, like so work with the record model that requires a certain overhead with constraints. So just for what it's worth, just throwing that out there, just to help you use constraints as a useful way of optimizing your programs. It looks like most of the questions have been answered. I'm just going to take a chat. Yeah, it looks like, thank you, Haruka, actually, for mentioning this. It looks like the IntelliJ plugin might not be updated to support the latest grammar. Yeah, I think I see that return then finalize might not be there. Yeah, thank you for calling that out. Actually, we will push out an update for that. Seems straightforward to do. Yeah, I'm gonna give people like another 2-3 minutes in the interest of time, instead of the full 10. If you do need more time, just drop it in the chat. It'll at least let me know. Great, cool. I think we'll, in the interest of time, we'll keep pushing forward. So here's our solution. Just to go over it pretty quickly, it's a transition called calculate. Takes in a principal, takes in a rate as specified. We declare a variable called amount for the principal, and then simply just construct a for loop. Be sure to do the multiplication first and then the division, and then return the value. This should be fairly straightforward. But let's sort of extend that a bit. One thing that's kind of sucks about this design is that you can only do for 10 iterations, and that seems very restricted and not useful. So the next extension on this challenge is, okay, can we vary the number of periods over which we accrue interest? So here's its challenge. Modify calculate so that it takes an additional private parameter called periods. Check that periods doesn't exceed 50, and then calculate the interest for those number of periods. So one thing that, just a hint for people, is that we have asserts, which are great for checking. And yeah, this one I'll give a couple minutes just for people to play with, and then here's some test cases. For these test cases, I guess it's worth mentioning. The first element is a principal. The second element is the rate. And then the third element is the number of periods. That rate, because we're sort of assuming like a division by 100, and it'll change if you do, depending on your like division factor. But if you're doing like divide by 100, it's 5%. Yeah, this should be straightforward as well. No tricks in this, but just want to get people familiar with the language. So we'll give it another 30 seconds, given that there's no questions in the chat. So there's a question out there. Oh, I see. Okay, it looks like our IDE plugin might be having some issues. So first question was, why does my VS Code theme when I open a Leo file? That's the plugin that we have. It kind of does the same like color scheme as Leo, like that we have for our language. So I believe you could be able to change that in your plugin settings. I'm not sure though. I've never tried it. So that answers the first one. The second one. Loop bound must be okay. So first one, unknown function assert. If it's coming in the IDE, this is where I mentioned the IDE plugin might be out of date. If you go through and run Leo build and you're using the most recent version of Leo, you should be able to. It should be able to run, no problem. Assert let me go. Maybe I'll leave this up here, but assert and then just a predicate is supported. I see another one. Loop bound must be a literal. So if you have your loop bound as an expression of something, it won't work. And the reason why is especially if that expression is an input, it's not statically defined, right? So like if you decide to pass in 5 or 10, you'll be doing a different number of loop iterations. So for that, you need to do a different sort of trick to get around it. And maybe the hint I'll give is maybe define a bounded number of iterations. Can you define an upper bound and then go from there? And I guess since there's some questions and stuff, I think we can give some more time. But one thing I'll call out here is that with circuit languages in general, this is an interesting sort of programming paradigm that people you'd need to adopt because your computation needs to be fully sort of specified and needs to be sort of fixed size in some sense. You need to sometimes employ a clever trick or something to get around variable inputs that might change the size of your program. So I'll give it another 30 seconds. Cool. We'll keep moving on. So here we have a solution. Here's our solution. Just to call out the different points here is that we've added in a third parameter called periods. And then we assert the first line is we check that periods is less than or equal to 50. And the main modification here is that we just add a condition inside of our loop that returns if the number of periods is equal to 50 or if the loop counter is equal to the number of periods or greater. It's greater than or equal to the number of periods. And yeah, that's sort of the simple solution here. The main idea we want to call out though is for loops at least, right? We need to still sort of create an upper bound on the number of iterations that we can do. And then inside the body of the loop or inside the program logic, we can encode ways to get the result for the variable amount that we wanted. And this is sort of the high level concept that we want to, the high level takeaway that we want to point out for this exercise here. All right, let's go on. And now let's actually start doing some cool stuff. So we talked a lot about records, why you need records, and how they support private applications. So we're going to get to actually program with them and play around with them for a bit. So first, let's kind of walk through how we can actually use records and declare and use records. So here we have a record declaration, and you'll see that it's very similar to the declaration of a struct, but records have two required fields, the owner and gates. Owner is the address that owns that record, and it's the address to which that record is encrypted to when it's on chain. So only that address, whenever you produce a record, and it's put to chain, or whenever you, if you're trying to consume a record, only if you own the private key corresponding to that address can you decrypt and use that record. And it's really important for getting this privacy property that we care about. And then we have gates. Gates is a denomination of Aleo credits, which is the native unit of currency on the network, effectively. Gates is effectively Gates is to Aleo credits as GWay is to ETH, as cents is to dollars, is the analogy there. And great. So with records, we can essentially use them to encode application state. Because we have this sort of owners field, and because of the way the protocol works, users exclusively own their own records. And records, like we've discussed before, enable concurrency and privacy. So let's see how this works. We'll walk through a couple examples and then build an application that uses records on our own. One thing to call out here, though, is so records, you can define also user data. So here on the left, you see we have some struct called payload, which is structs as we discussed earlier. And we have a record here on the right, state, which takes in the field, which is in itself a struct called payload. And records can take multiple number of data fields. This one only has one, but then you can, if someone wanted to, they can define another data field under it, foo, that takes in a U8, and so on and so on. We do have some static bounds right now while we're kind of going through early phases of testnet, figuring out what programs can be deployed, ironing out the kinks. But there's a static bound. I believe it's 32 if you're interested. But if it does start to hinder your application, we'd love for you to file an issue, and it'll let us know that people are hitting into this limit, and we are open extending it. Cool. So this is how you declare records. It should just be the TLDR is add owners and gates, and it's like structs. So how do records work on Aleo? So we talked about transitions. Transitions are the public interface of your contract. Transitions are the pieces of code that can interact with on-chain objects. So a transition can take in some number of records and produce some number of records. So let's see how this works, how you can do this with an actual program. And with every project, right, we'll talk about tokens and how do we instantiate a token on Aleo using records. This token will be private by default. So essentially you can think of a short blurb here is how do you instantiate Zcash within an Aleo program, something Zcash-like. Before I go into this example, I'll take a pause. I see some questions. There are use cases for having a record within a record. This is sort of unexplored territory. See, records are explicitly on-chain objects, right? Or objects that live on-chain. If you'd like to store the data of another record in a record, you can totally do that by pulling it out of one and putting it in another. But right now, because we're kind of conceptually thinking of them as blobs or encrypted blobs on chain, it's a question of what does it mean for a record to be in a record? Is it a reference to another record? And then a question we'd have to kind of ponder is what's the use case? So really the short answer there is we don't know. And we're curious to find out. If you have some thoughts on this, we'd love the feedback because it'll really help improve and think about what an alternate construction looks like. Is the code from this session shared in a GitHub repo or anywhere else? In Aleo HQ, which is our main GitHub repo, there's a workshop repo for it. I'll let, I think maybe someone link it up in the chat, but yeah. Final question before we go on is, does Leo provide some sort of random number generator or a suggested approach? There's nothing right now for an RNG natively right now. So, but it's something that we're interested in. So if you have a proposal or you'd like to see this, please feel free to file an issue or file a proposal, and it'll help us track this issue. All right, so onto records. So we have some record token here, and token will have an owner and gates as required, and then define a balance. Token will also have a function called transfer. So transfer, what it's going to do is take in a token record as input, an address that you want to send to, and an amount. And then you're going to, starting on line 2, compute the difference, the amount that you're going to send and the amount left over. You're going to create a new record called remaining with the difference, the stuff that's left over. And one thing to call out here is because Leo has safe math by default, checks for overflow. We don't need to check for overflow explicitly on line 2. And then on line 8, we create the token that we're going to send to the other party. And that will be encrypted under their address, which is the receiver. And then send those tokens out, return them. And how does it look like with some like on-chain interaction? Let's see. Oh yeah, just to call out. That's how you instantiate a record in code. So let's say you have some ledger with some record N on it. The owner of that record is Alice, and only Alice can see that record. It's encrypted to her address. So if Alice wants to send some number of tokens to Bob, let's say she wants to send it via transfer, she puts in as input her record, and she can do so because she can decrypt her record. She puts in Bob's address and the amount of tokens she wants to send. The transition transfer will produce a new record, being the remaining amount for Alice, and the amount for Bob. That's record number 2. Notice that record number N1 is new. It's a new record. It doesn't use the same one, record N. And both these records are encrypted under their owner's address. The transition transfer also creates a proof that the network can check to make sure that this transition is valid. And if the network checks and the proof goes through, these records are appended to the ledger. Now, one thing to call out here is that we see that record N is grayed out. And this is something fundamental about the record model. When you use a record inside a transition, it's used and cannot be used again. This is where the ledger prevents double spending. If you did allow this, you actually get into some pretty interesting attacks. I think it's pretty straightforward to also construct one. So essentially, what you're doing here is that, so you can, when you spend that record, it still stays on chain. The chain keeps track of it, but it tracks it with a serial number that tells you that that record's been spent and cannot be used anymore. One question I see is, for records, are you only able to encrypt with your private key, or can you choose to encrypt with other owners' public key so that they can only decrypt it? And that's exactly what we did in this program transfer, right? So like essentially in this transition transfer, this is something that Alice is going to call, but she's going to provide Bob's address as input, right? So she essentially, that in line 8, when you create that token transferred, you're creating a new record that is encrypted to Bob's address. Now, Alice, because she called this function, she knows how much she sent to Bob. There's no way to get around that. But Bob, like when this record's put on chain, only Bob will be able to decrypt it. And if Bob has been scanning the chain for records that are now created to him, he'll sort of be notified when this record's included. Cool. Sweet. So that's how records work. And now we're going to do another programming challenge here. For purpose of time, I'm going to maybe keep this one pretty short. So try to follow along if you can, but there is our workshop repo, which we'll do this exact example. So if it's a little too fast, don't worry, you can go back and do it yourself. And then as always, if you have any questions, please feel free to hop on our Telegram or Discord, and we're always there, happy to answer. So here what we're going to do is implement a private auction using Leo. And in our design, where we care about privacy is that we don't want bidders to learn any information about each other, but we're okay with the auctioneer, the person running running the auction, to see that information. And we're assuming that the auctioneer in this sense is semi-honest or is trusted. The auctioneer isn't colluding with any players. It's not revealing some information on the side. So That's just how our trust model is going to work for simplicity's purpose, simplicity's sake. And yeah, let's kind of walk through this model, like how we want this to work effectively. So the first step, we want to create some sort of transition place bid, which Alice can invoke, and it creates a new record, which is encrypted to the auctioneer's address, and that contains some information about Alice's bid. Then we want Bob to be able to call that same function, place a bid, which also creates a new record that's encrypted to the auctioneer's address. Once the auctioneer decides to like finalize the whole thing, or like start resolving the auction, they can take in the two records that were created from Alice and Bob, top and bottom respectively, and push it through a transition called resolve. Resolve will select the winning bid, the bid with the greatest amount, and produce a new record, which is essentially the same as, just the new record is whichever record was the max bid. So it's going to still keep the owner as the auctioneer, going to keep the same amount of gates, going to keep the same metadata associated with that record, but it's just going to select the maximum one, and in the sense, selection actually produces a new record, but that's just a technical detail underneath. Then the auctioneer is going to finalize the winning bid or finish the auction. And what they do in this transition finish is it takes in the winning record and outputs a new record, which contains the same payload as the old record, but encrypts the new one under the winner's address. And in doing so, that winner now owns this record that they can show and attest to that they are in fact the winner, and then can use it, maybe when they're resolving the auction on the side, or out of band. So let's see how that works. So let's kind of go through the challenge. We're going to go through this a little quickly, so don't worry if it's a little too fast to follow for now. So we're going to create a new project auction. We're going to define a record called bid, which has the following user-defined fields: bidder, amount, and his winner. And yeah, I think I'll give just a little bit here. Let's see if there's any outstanding questions, but okay, first question, randomness on chain. We don't have any functionality baked into the core for now. We're interested in doing something like this, so feel free to file an issue, or if you have some proposals, we're willing to kind of work and workshop that and make that part of our language. Are the source code of transitions necessarily public? So if you use the protocol as is, you publish a program and everyone else can use it, and and so in doing so, you do make your source code public. This is because like in the Snark construction, your predicate is also public. But what you can do, and this is something we're also interested in doing, is eventually, like if you want to keep your source code private and just check proofs on chain, that's a totally feasible and reasonable thing to do. How can the function transform or change, manipulate Bob's record since it has not been decrypted with his private key? Does this mean you can only send tokens to an address? So like the function transform, I think you were maybe referring to the function transfer. So the function transfer is not manipulating anything to do with Bob's records. It's just producing a record to Bob. It doesn't take in any of Bob's old records. So because it's doing so, it's just kind of like, it doesn't need Bob's key to like run effectively. Next question, is there a way for an auctioneer to commit to its program or give the participants any guarantee? Yes, it totally can. When the auctioneer publishes their program on chain, that is effectively the source code of the program that's run. So when you're doing place bid, that's the program that you will be running. And then finally, perhaps a naive question. In this setup, the auctioneer can see all of the bids. And yeah, this is correct. To find the winning, yeah, the auctioneer can see all of the bids. Is there a mechanism to minimize the number of bids that the auctioneer can see, but still find the winning bid? Just wondering how much privacy there can be in this situation. So let me think here. So one interesting way you could probably extend this scheme to increase privacy is maybe construct like an MPC or just add some notion of multi-party computation to it. So instead of like giving the auctioneer all the responsibility to resolve and do things, you just have, you can sort of do the compute together and hide some information from the auctioneer. I'm gonna kind of leave it at that high level because MPC constructions are really bespoke. So yeah, we'll keep it at that. I think, great. Awesome. I'm going to keep moving, and actually I'm going to sort of jump ahead because we'll be coming up on time soon, and we want to make sure we have time for everything else. So here, we define a record. The main things to call out here is that there's a bidder, there's an amount, and there's a winner, all of which are primitive data types. So the next thing we're going to do is create a transition called place bid, which takes in the bidder, the address of the bidder, and the amount bid. It checks that the caller is the address of the bidder, and then constructs a new bid, which is owned by the auctioneer. And the specifications here, I'll post all these slides up, but for the purposes of this workshop, or just for the interest of time, I'm just going to push through, show the solution, and we'll talk about some more stuff, some more interesting stuff. So here's a function place bid. Line 2, we do an assertion check and simply just construct a new record on line 3. Then the next part, the next function that we're going to define is a function transition resolve, the one that the auctioneer is going to call to resolve the bids. This will take as input 2 bids and then check that the invoker of this function is only the auctioneer, and selects the bid with the highest amount. So this is actually very straightforward to do in Leo. You just have a check on line 2. It's an assertion check, checking that the auctioneer's address, the caller's address is as follows, which is auctioneer's. And then, just does a simple conditional statement and returns the greater bid. And then finally finishing the auction. So we're going to define a transition called finish, which is going to take a bid as input, and then just produce a new record that has the same payload that's encrypted to the new owner. And the way it does that is, same thing, line 2, there's a check, and line 4, there's the result of the bid. So with that, I'm going to see if we can quickly run through one more concept, which is on-chain state, which is a new exciting thing that we have on Aleo, where we combine some of these notions with the account model, with the record model, to get like this hybrid model where you can do all your private stuff in private land and record land, and use on-chain state when it's needed and it's useful. On-chain state and sort of like ledger re-execution can be useful in certain situations where you want the network to be executing on your behalf. And maybe for certain applications like escrow, this is very naturally motivated. So Leo has this thing called mappings. And for those coming from Solidity, this should be a very familiar interface. Mappings are essentially on-chain pieces of state that, a map from a key to a value. Should be very straightforward, especially if you are referring from, Solidity, the EVM and whatnot. So with mappings, we can do something like a transfer of a token, but maybe we can start with a token that's in a record, an amount in a record, and transfer it publicly. So I have a private token that I don't want anyone to know how much balance it has, but I want to publicly send some coins to some other party. And I don't care if people know how much I send to that other party, but at the end of the day, they don't know how many tokens I have in total. And we can do this by combining the record model and mappings. Here we've defined an augmented version of our transition transfer, where instead of receiver and amount being private, they're actually public values. So everyone's going to know who I'm sending it to, how much I'm sending. Line 2, we calculate the difference as we've done before. But then the important thing to call out is line 8. So in line 3, we create a new record with the remaining balance, send it to ourselves. And then in line 8, we return that record, but then invoke a finalize block, which is what you see with the syntax then finalize with the arguments receiver and amount. A finalize block is essentially a piece of code that tells the network what to do when executing this transaction on chain. So once you do the off-chain component, get a proof, submit the transaction, the network checks the proof and then executes the finalize block. And we'll go through an example of this, how it does this. But what we're doing here is then in lines 10 to 12, we're incrementing an on-chain mapping called balances with the receiver's address and the amount that we sent them. So in this way, the whole network knows what that new person has and is able to see that the receiver got some money. And we'll kind of walk through this in a quick flow. So here we have a network. There's some validators checking the network. And you have a ledger, which contains a record with Alice's balance. And you also have an on-chain mapping. This is public state with keys corresponding to the addresses, both Alice and Bob's, and the values that they have. So step one, Alice will query the network for her encrypted record. So she's going to get a record, pull it from the network. It'll still be encrypted. She will then decrypt her record and execute the transition transfer locally. So she's going to put in Bob's address, the amount she wants to send. These will be public. And then the transition transfer, the one that we just discussed, the modified one, will produce a new record containing Alice's remaining balance, a proof that you see at the bottom, proof pi, and then also send, also produce or just pass through the public inputs to the finalized block. In this case, Bob's address and the amount she wants to send. This all will get packaged into a transaction that you see here. The transaction will contain the record. It'll be encrypted under Alice's address. The proof is also included, but the Bob and the address are set in the clear. So what the network does is it checks the proof, and then if the proof verifies, if the proof doesn't verify, network doesn't do anything, no state is updated, just dump the transaction. If the proof does verify though, the network can add the record to the ledger, say that the old record was spent, and also update Bob's balance up here in the corner with the new value. And so the network executes the finalized block and stores the new record. And this is essentially a powerful model which really sort of allows you to, as a developer, choose how much privacy you want in your application. So it's really like a nice fine sliding scale that you can use and define what you need privately, but then use public stuff when it's useful and necessary. And this can be a powerful primitive. We're really excited to see what people can do with them. I will give one big asterisk. Mappings are an extremely experimental feature. There's a lot of improvements that we as a team are really focused on doing, but more to come over the next couple months. So we have a little bit more time to touch on a couple things. First, we'll talk about some tools that are available in the Aleo ecosystem that can help you run, check your programs, just improve the developer experience. And then we'll finally wrap things up with an announcement on zPrize. So first, deploying applications. What's the state of it right now? So right now, we're working on adding support to testnet 3 to actually send your transactions, actually deploy your programs, execute them on the network. But in the meantime, we have a little tool. It's an experimental tool called Slingshot, through which you can create a node and a local development node and run it and play around, deploy, execute your programs. I see there are a couple of questions. So I'm going to pause here for a second and just answer some things. Let's see. Do mappings conflict with concurrency properties? Yes, they do. So because you have to do things, so they don't conflict with concurrency properties, but they're subject to the same concurrency and consistency properties as Ethereum state, effectively. So the order that is determined by the block is sort of the order in which finalized blocks are executed. If you don't design your data structures in an idempotent way, or maybe design them as operational transforms, you'll have a problem with on-chain consistency. And then, is there a way to achieve in the finalize action? Yes. So this is what this question is asking is, can you do general loads or stores in finalize state in finalize blocks? So right now it is not possible, but this is the improvements to the mappings that we're really actively working on. So so more to come, stay tuned, but yeah, we're really excited to see what we can do there. And we'll post an update to the community when that's ready. So in this presentation, just switching things back, I wanted to show a demo of Slingshot. We're a little bit tight on time, but you can go to this GitHub repo where you can look at the Slingshot tool. And after this workshop, I'll post some better instructions and some resources in running this tool and kind of using it locally for those that are interested. We're going to skip ahead and talk a little bit about formal verification, which is an exciting component that we're adding into an exciting direction that we're exploring. And to do that, I will have Alessandro, another one of our engineers, come up and present on it.
Hello. Okay, I'm going to tell you very briefly about the work we're doing on formal verification, applying it to the Aleo blockchain, Aleo programming language, etc. So first of all, the motivation for this is that the zero knowledge proof that we've been talking about concerns the fact that the computation was performed correctly. But what is the computation described as? It's described as a zero-knowledge circuit. It's essentially an arithmetic circuit where gates are algebraic operations and so on and so forth. You can read all about that in the literature. But the point is that that's what the zero-knowledge proof refers to. However, the user does not write directly the zero-knowledge circuit. The user writes some Leo code, and according to our tool chain, the Leo code gets compiled to Aleo instructions, which are this intermediate language that we use also to store programs on chain. And then Aleo instructions are compiled to the zero-knowledge circuit. Also, there are two major steps, and within each of these steps, there are a lot of sub-steps, as is typical in compilers. You first parse the code, you type check it, you do some transformations, optimizations, and so on. So you can imagine each of these two arrows really consisting of a lot of smaller arrows sequenced together. So how do we know whether the zero-knowledge circuit is computationally equivalent to the Leo code? So how do we know whether it was compiled correctly? So that's a general concern, obviously. You always want your compiler to be correct. But for this particular application area, the point is that if the compilation is not correct, then the zero-knowledge proof does not necessarily apply to the Leo code. It still applies to the zero-knowledge circuit, but that may differ from the computation as intended by the user who writes the Leo code. So in order to address this problem, we use formal verification. So what that is that we were building tools to generate theorems, mathematical theorems that assert the correctness of the compilation process. Since there are these two major compilation steps, we generate one theorem for each of them. Those are fairly independent, but of course they get combined together to give an end-to-end assertion and of correctness. And to do that, obviously, we need a formal semantics of all these languages and formalisms involved. So we are developing a formal semantics of the Leo programming language, formal semantics of Aleo instructions, formal semantics of zero-knowledge circuits, those that actually we already have and we are using. And so when we generate these theorems, and then we have them checked mechanically by a theorem prover. So we don't do that by hand. We don't just write them in pencil and paper. We use tools to do that. Specifically, we use the ACL2 theorem prover, which is one of a handful of the main general purpose theorem provers in the world. It's it's industrial strength. It's used a lot in hardware verification in commercial companies, also increasingly in software verification. And so we are building the theorems are expressed in the language and logic of the ACL2 theorem prover. And once we generate the theorems, we ask the theorem prover to check that the theorem is correct. Of course, we need to spell out the proof in sufficient detail so that the theorem prover can check it. And when I say proof, I don't mean zero knowledge proof. I mean a proof of a mathematical theorem. So it's at a different level here. So this is very much work in progress. We have already some of the pieces done and working. Right now, we are focusing mainly on the verification of the zero knowledge gadgets, which are essentially components that get composed together to generate a zero knowledge circuit for given Leo products. We also have other parts done and in progress in the front end for both Leo code and Aleo instructions. So yeah, we will publish more updates on these as soon as we have them available. We're actively working on that. Having said that, I'll ask Pranav to come back.
Great. And with that, just a quick blurb on our project and how to get involved. So Aleo is proudly written in Rust. We're open source on GitHub. We have our workshop, repo with all these code examples posted up here. And we have different ways through which we engage with our community: Twitter, Discord. We also have a Telegram that's not here, but we can put that up somewhere for you guys to get access. We'd love for people to contribute to our project. So whether that means filing issues, filing bugs, writing their own features, those are all welcome. If you'd like to contribute in a more formal way, we have a grants program where we'll workshop and come up with a grant proposal, or you can come up with a grant proposal and we'll fund it and have a more collaborative engagement. We're also hiring, so feel free to go to Aleo and we have our jobs postings on there.